We have Jan from Facebook, who's going to talk about how he's been developing Facebook's internal hack GraphQL server that powers their production mobile apps. He's going to talk a little bit about how they made it performant enough to handle all those requests, and also what it takes to build a GraphQL server that so many developers can collaborate on without stepping all over each other. So please, Jan, take it away.
Hey everyone, I'm Jan. First of all, I want to thank the Meteor team for inviting us all here. I'm very excited to be here. It's my first time at one of these community meetups. Hopefully not the last one. I think the original plan was that Lee Byron would come today and speak about the RFC process. So if you were hoping for that, I have some bad news and some good news. Bad news is Lee's in London, so he couldn't make it here. Good news is he spoke about that at the London GraphQL meetup, and there's the recording. So I highly recommend it to watch that. There are some links here. Make sure you memorize them before I switch to the next slide, because you'll never see them again after that. So anyway, so I'm gonna tell you today about what it takes to run what's probably the world's biggest GraphQL server. Right. So I work on the GraphQL server team at Facebook. So a little about what that entails. So my favorite feature of GraphQL is that it's a language designed for client developers. Our goal is to build the ideal language you always wish you had if you're a client developer. So obviously a big part of that is just making sure we achieve that goal or get as close as we can. So client developers are big customers of us, not just on the server team, but on the GraphQL team in general. But then, especially on the server team, we have another very important group of customers, and these are the server developers, which may or may not be the same people. Sometimes there are, sometimes there aren't. So these are the people who build, I don't know, backend services, and they want to expose them over GraphQL. So what we need to do for them, the perhaps primary goal is that we need to make the framework easy to use. So that means the abstractions that we build should be easy to understand. It shouldn't require tons of boilerplate to expose some simple concept like a new type or a field using GraphQL. That's one of our goals, but there's another, perhaps equally important one, and that's that we are sort of the shield that guards the realms of man. We're responsible for making sure our GraphQL schema is sound and sensible, and that it stays that way. So for that we employ a variety of techniques. Mainly, we try to make the abstractions. We try to design them in such a way that it makes doing the right thing easy and doing the wrong thing harder or ideally impossible. But then we also have a ton of things like lint rules. For example, if you create a new field that looks like it might be an ID because its name is ID, but you try to give it a type of string or integer, and we warn you that this field should probably be using the ID type. And then we have some even more fancy tools. Like for example, if you try to commit a change that would not be backwards compatible, we have this bot that will show you a warning right there on the revision. It'll tell you that we're removing some field that clients might still be querying for. So that's part of what we do. But another important part is that we also care a lot about efficiency. So since, like I mentioned, GraphQL is designed for client developers, a lot of time that means we have to make trade-offs where to make things easy for the client developers, we do a lot of work on the server. So as frameworks go, GraphQL is not particularly cheap on the server. We have to do a lot of work on the server. It involves anything from parsing the query, validating it, to make sure there are not like, I don't know, infinite loops of fragments, to formatting the response and all that. So there's actually a significant overhead of the GraphQL framework. I think even in our somewhat optimized implementation, it's something very roughly on the order of 10% of CPU time in a GraphQL request could be considered the overhead of the GraphQL framework. So we're happy to pay this cost for all the advantages of GraphQL, but it's not negligible, and it's important. doing even small optimization there can have a lot of impact. We can literally save millions of dollars at our scale by making some fairly minor optimization somewhere inside the internals of our GraphQL server. So since the topic of the day is experimental GraphQL, I'd like to frame the rest of the talk as an overview of some things that we've experimented with over the past few years. So there'll be a little of everything, but you'll see that most of what I talk about will fall into some of the categories I just mentioned. So it'll either make things faster or easier to use for some group of our customers. And I'll start in 2015, which you may remember as the year GraphQL was released. The GraphQL open source specification was released. And you probably know that we've used GraphQL at Facebook before then. And the version that we used before was actually somewhat different from the one that we released as an open source specification. So this process of formulating the open source specification was a very good opportunity for us to revisit some of the older design decisions, or in many cases, not as much decisions as just like how things evolved over time. And this ranged from trivial things like minor cleanups in the GraphQL syntax, all the way to significant changes that change the semantics of the language or change how the language is used. I'll start with some examples of the former. So here on the left, you can see a query or part of a query in our legacy GraphQL syntax. And on the right, you can see the equivalent part of the query in the open source syntax that you're familiar with. The interesting thing to notice here is that in our legacy syntax, GraphQL fields didn't have arguments. They had calls, and those calls had arguments. So this is a kind of an interesting change. It's not strictly better or worse, it's just different. It makes some things easy. It made some things easier to express. For example, here you can see that the version in the open source GraphQL is not it's more verbose, and it also maybe allows some weird cases, like what if you specify the month but not the day? How do we resolve that? So then we'd have to come up with workarounds that, again, result in more syntax. But in the end, we decided that this extra interaction of having calls and calls having arguments was probably not worth it. It also led into weird edge cases, like what does it mean to have a call that has no arguments? Like, what does this represent? So that's an interesting example. Another thing I'd like to show you we had something called root calls, which sounds similar on the surface, but is actually quite a different thing. It shares the syntax with the calls that I've just showed you. And the idea is, you know that each GraphQL query starts with the root field, which starts with the root object on which we can query for some fields, and then there are subfields and so on. So in our legacy syntax, that wasn't the root field. That wasn't the root object. That was a root object. So each query started with a different root object, and the root call was sort of a resolver that would produce the root object at which the query should start. So you can probably guess that as part of the migration to open source GraphQL at Facebook, we just converted all the root calls into fields on the root object. I think this was a welcome cleanup. No one is really missing the root calls. So this is a nice thing that simplified the language without really losing anything. All right. You're all familiar with fragments. They're a very good way to conditionally include parts of the query in the response, depending on the runtime types of some objects. What you probably don't know is that fragments, well, originally they weren't part of GraphQL at all in the very first version, but then when we added them, at first they didn't actually have a type. They were just a simple way to reuse pieces of GraphQL code. So fragments, as you know them now, there was a feature that we called conditional fragments, and that only became part of the GraphQL language later. But people liked it so much, and it was so useful that eventually, in the open source specification, that became the only way to write fragments in GraphQL. And there's an interesting point to mention here, in that since we need to preserve backwards compatibility to support all the old clients that are still out there in the wild, we had to include some way for our new server to support these unconditional fragments. So we have a special directive for this. And this is probably the reason why directives are such a prominent part, or have been such a prominent part of the GraphQL specification from the start, because we really need them to support all these legacy use cases in our server. And then one more thing that I'd like to mention. This is perhaps the most important change from legacy GraphQL to open source GraphQL. This is not a syntactic change, it's a change in behavior. The old GraphQL had this behavior that we call fed interfaces. It means that if there's an object, or in this case a root call that resolves to an abstract type, like node here, which can resolve to basically anything, then you could query for any field on that, as long as that field exists on any subtype of that abstract type. And then our server, if the type exists on whatever the runtime type ends up being, then we give you the response, otherwise we just give you null. So that kind of sounds simple, but it has some disadvantages. The perhaps most obvious disadvantage is that this can lead to overfetching. For example, if the intention here is what in an open source GraphQL would be expressed as this, that we want to, if this node is a user, we want to fetch the name and friends, and if it's a group, then we want to fetch members. This can result in overfetching because groups probably also have names, so we would fetch the name of groups here as well, even though that's not what we needed. So it can result in overfetching because of things like this. But there's a more subtle but much more dangerous disadvantage, and that's this behavior enforces that all subtypes of a specific abstract type, they all have to be consistent with each other. So if any type of node, for example, has a field called location, then any other type that also has a field called location, that field has to be consistent. It has to return the same return type. It has to have the same set of arguments. And this was a huge pain, and it still is a huge pain for product developers because we still have to support this behavior because of legacy clients. But this is something that without fed interfaces wouldn't happen, and we would have completely avoided this problem. So we're trying to get to a state where fed interfaces are a thing of the past, but we're not quite there yet. Now, all these things that I've showed you, at this point you're probably wondering like how were we crazy or what? The old version just seems so much worse than the new one. But and that's if you look at each thing separately, that probably is true. But if you look at these things together, like this combination of how unconditional fragments and fed interfaces would be used and work together, it actually kind of makes sense. It forms a system that is internally coherent. So here we're querying for a node of an abstract type. We have a bunch of unconditional fragments that are therefore always included, and thanks to the fed interface behavior, this is not a problem. We can fetch for all these fields, which may or may not exist on the type. So it kind of makes sense together. But I think it's probably agreed that the version we ended up with for the open source release is probably preferable. So that's an overview of what we experimented with at the time, around the time we were working on the open source specification. Now, forgot to mention that this presentation is like one of those nonlinear movies where time skips back and forth, and you have to put it all together at the end to make sense of it. So now you should be imagining a cutscene with some ominous music in the background. I'm gonna jump a few years back and cover one lesson that we learned, probably the most important lesson that I'll keep going back to later in the presentation. And that's that the best GraphQL server is one that doesn't actually accept GraphQL queries at all. So we don't want clients to send us GraphQL queries. What we want clients to send us are just IDs of what we call persisted queries. That means that for any queries that our clients want to send us, we store them in a database on the server, we give them an ID, and we ask the clients to send us this ID instead. So this has the obvious advantage that we save a lot of bandwidth, especially on slower networks. Some of our queries are pretty big, I think going into maybe hundreds of kilobytes, or tens at least. So this saves some bandwidth, but it enables lots and lots of other optimizations, like some that I'll mention later. So let's go back to the present, or last year. The main thing that we worked on last year was we were building a new server runtime based on the open source specification to be used as replacement for the old legacy GraphQL server that we had. And this was, again, a good opportunity for us to revisit the various things about how the old server worked. And in this case, it was mostly concentrating on performance, making things faster. So first thing, let's talk about parsing. Parsing is a pretty big chunk of the overhead of GraphQL. I think even after some of the optimizations I'll mention, it's still something on the order of 10% of the overhead. That's a very rough number. So it's pretty costly. And the obvious thing you can do there is that we realized that we're probably executing the same GraphQL queries over and over again. For example, something like the newsfeed query from whatever is the current version of Facebook for Android, we'd be executing that over and over again. So let's not parse it every time. Let's just parse it once and store it in memory in its pre-parsed form. So to see how much we could save with an optimization like this, we would look at some data. So this is a chart that shows what percentage of production traffic would be covered if we stopped parsing the top X queries. Now the exact numbers here are not important. What I just wanna, which is you probably don't see them anyway, but what I want to show you is that it's clear that we can gain big advantages from storing the first few queries, and then we quickly get into diminishing returns where we can store hundreds of more queries for only covering a small increase in percentage of production traffic. It's amazing how smooth this graph is, right? You wouldn't believe this is actual data. Yeah. So based on this, we arrived at a kind of a sweet spot where if we store the top 200 queries that we see in production at any point in time, if we store these in memory in their pre-parsed form, that means we wouldn't have to parse anything in about 70% of the GraphQL requests we receive in production. Of course, the top 200 queries change all the time, so we have to recompute what those are, like daily or even multiple times a day. But this is still always true. So we actually have this right now. At every one of our web servers, a chunk of memory is dedicated to storing the pre-parsed form of whatever the top 200 GraphQL queries are at the time. So this is one good optimization that allowed us to save over 2/3 of the parsing CPU cost. Another optimization was that we don't always have to parse the whole query. A typical query consists of one operation and then a lot of fragments, tens or even hundreds in some cases. So let's just start by parsing the operation. And if we start executing the operation and then we run into some fragments that we need to expand, we just parse them at that point. So this is another useful optimization. And then at some point we ran out of these clever ideas that we could implement. So we just had to put our heads down and just optimize the shit out of the parser that we had. So just to give you an example of the kind of thing we did, this is an example. This is a chunk of code from our actual production GraphQL parser in Hack, which is sort of an enhanced version of PHP. And you can see some pretty crazy optimizations here. For example, the conditions in the loop are ordered by likelihood. So since the most common type of white space we see is a space, we check for that first. And then it probably short circuits, and we don't even check for those other types of white space, like carriage returns, which we don't have at all, or tabs. Or even we found out that in a HHVM, which is our virtual machine that runs PHP or Hack, it was more expensive to access instance variables than it was to access variables on the stack. So we would, at the beginning of this function that needs to access them multiple times, we would copy them into local variables on the stack and then copy them back at the end. So with things like, with optimizations like this, we were able to, from the naive or initial prototype implementation that we had, we made it faster by something like between 2/3 and 3/4. So if you put this all together, you can calculate that we made the parser about probably around 10 times faster than it would have been without any of these optimizations. So since the parser is now 10% of the overhead, you can imagine that without this, it would be half of the overhead. So that would be pretty crazy. So this is some pretty good stuff. Another thing that the GraphQL server does is validating queries before we run them to detect things like when you're trying to query for fields that don't exist, or if you have an infinite cycle in your fragments, things like that. The optimization we did here is actually pretty simple. We just don't do it. So the idea here is that since most of our queries are persisted queries, we only get an ID. We don't need to parse them every time. We don't need to validate them every time. We just validate them once at the time they're persisted. And then when they're actually run in production, we already know they're valid. So there's just no reason to do it again. So we don't even need to optimize this. We just don't do it. Then another thing that the GraphQL server does, and it also accounts for a non-trivial chunk of the overhead, is something we call defragmenting. It's when you have an object with a bunch of fields and maybe multiple fragments, possibly nested fragments, and you're trying to actually generate the response to send to the client. And we need to merge all the fields from the different fragments. And so merge all the fields from the different fragments. So this seems like another good candidate for memoization. Like maybe there might be fragments in the query which are included repeatedly or things like that. So this seems like something that we could also memoize. But wait, not so fast. This is a screenshot from the open source GraphQL specification. This is the relevant function that is this is the function that's responsible for doing this part of GraphQL execution. And you can see that this function has 4 arguments. One of them is a selection set, which is actually a list of nodes that might be arbitrarily long. So like even calculating some kind of cache key that we could use to memoize the values that this function calculates, that would be a non-trivial amount of work. Probably it would cost more than we would even save from the memoization. So the first thing we would even need to do before we even consider this is figure out a way to make this function more memoizable, so to speak. So the function header we actually ended up with looks sort of like this. It's actually pretty similar. Has the context, which just has the variable values, the parent type again. But then instead of the selection set, we figure out that the selection set must come from somewhere in the original GraphQL query text. So instead of trying to calculate the memoization key based on the selection set, we just store the one node it came from. But wait, actually, it's not always one node. In some cases, that might be multiple nodes because of these fairly complicated merging behaviors that can happen in some cases. So this actually has to be a vector of parent nodes. But in most cases, it is indeed just one node or very few nodes. So this is a small vector, and it's pretty feasible to memoize on that. So now that we made it sort of memoizable, the other thing is we still had to consider whether it makes sense to memoize every time. Like, do we actually do repeated work that's worth memoizing, or would the overhead of memoizing just be a waste of time and memory? So once again, we looked at some data. So this is an analysis of one of our biggest queries, probably the newsfeed query or something similar. And it shows here that the majority of the selection sets that we defragment only occur once. The 454 selection sets only occur once. But there's a significant amount that occur multiple times. There's quite a lot that occur 2 or 3 times. Then it goes down, but there are a few outliers, like this one that occurs 211 times in the same query. So it seems that it might be worth memoizing sometimes, but maybe we want to be a little more clever and just not do it all the time. So the first idea we had was to just memoize for lists. So if we have a list, then the same selection set would be evaluated for every element of that list. So that was a good candidate, and we had some success with memoizing that. But over time, we were actually able to micro-optimize the generation of the cache key even more. And at that point, it became feasible to memorize even more often. Now we memorize always, but only as long as this vector of parent nodes only has one element, which turns out to be like over 90% of cases. So if it has more than one element, which is in one of those crazy merging scenarios so then in those cases, we just don't memorize it. And that seems to work pretty well. And the final optimization we've done that I'd like to mention. So if you think of the GraphQL schema, the type system on your server, it consists of a set of GraphQL types, in our case, thousands of them. Then each type has fields ranging anywhere from 1 to hundreds of fields. And the field in turn has some arguments. So it turned out to be really important for us to instantiate these lazily. So we wouldn't, every time we receive a web request, we wouldn't instantiate this whole schema with all the possible types and all the possible fields and their definitions and all their arguments. We would just instantiate whichever types or whichever queries, whichever fields were actually queried. And one specific example I'd like to show you is how we handle arguments. And first, I'll show you what it looks like in the reference implementation in GraphQL.js. So this is the relevant chunk from GraphQL.js that resolves the value of a GraphQL field. This function here, it constructs all the argument definitions for the given field and then coerces the arguments to the correct value of the correct type of each argument. And then we pass the coerced arguments to the resolver function. So this makes a lot of sense, but it actually wastes some work that doesn't really need to be done. So what we actually do looks sort of like this. So we rely heavily on generated code. We generate a super optimized resolver for every field in our GraphQL schema. And if you look here, you'll notice that this doesn't actually construct any sort of an object that would represent an argument at all. All we construct is an object that represents the type of the argument. So the first argument width is of an int type. So we have this generated hard-coded object that represents the int type here. And then we just use that. And another thing here is that we don't even do this if the argument was not actually specified in the query. So if there isn't a width argument in the query, then we don't even construct the representation of the int type. We just immediately store null in this variable. All right, so that's an overview of some performance optimizations that we've done that allowed us to make the new server even faster than the old one that we had. Now I'd like to move back to the present, or move forward to the present. What we're working on right now is that we're trying to revisit how server developers write these GraphQL definitions. By which I mean, the first part is what types exist in our schema, and how do they declare what types exist and what fields exist on these types. And then an even more interesting part is how do they create these field resolvers? How do they declare the chunk of PHP code that actually resolves the value of the field? One idea that sometimes comes up is that we could use the GraphQL IDL language, which I think is soon to be part of the official specification. So a developer would write the definition of their type in the IDL language, and from that we would generate some kind of stub, some kind of PHP class with empty functions that they would have to fill in. And then they would run some other build step that generates the super optimized runtime definitions, like the one that I just showed you. So this is one possibility that would be fully type safe. But it seems like a lot of steps and people never like having to do a lot of steps as part of their development, potentially hundreds of times during the day. And also, it would force everyone to learn this new language, this GraphQL IDL, which I mean, is not necessarily a bad thing. You could argue that you want people who write GraphQL definitions to understand GraphQL, but on the other hand, in some cases, it's good to have a lower barrier of entry. So we've been thinking of different ways to bridge the GraphQL and the Hack type system, or the PHP or Hack type system. So one idea we're experimenting with now is if we could just take the existing functions that people already have and annotate them using attributes so that they become exposed as GraphQL types. So here we annotate some class so that it is exposed as an object type in GraphQL, and annotate some function so that it is exposed as a GraphQL field. The GraphQL framework can infer pretty much everything that it needs from the Hack code. So this includes the types of the arguments, including things like which arguments are optional, which arguments have default values, and what those default values are. We can access all these using reflection in Hack and HHVM. And a big advantage of this, that we can get a lot of type checking for free from the Hack type checker. So if, for example, the developer tries to return something that's not an image from this function, it would be a type error, and it would be immediately surfaced to them. And we can take this even further. We can implement things like interfaces. So if we annotate a Hack interface so that it becomes a GraphQL interface, then any Hack class that implements this interface, if it's annotated as a GraphQL type, that would mean that GraphQL type also has to implement the respective GraphQL interface. So this is pretty neat because the Hack type checker enforces that both the Hack type system is sound and that the GraphQL type system is sound. So if, for example, they forgot to add a gen profile picture function here, which means we wouldn't know how to resolve the profile picture GraphQL field, this would be a type error that the Hack type checker wouldn't let in. So that's pretty neat. Another thing that people like to do is reusing their field resolver code. For example, let's say the profile picture field could be implemented in the same way on different types, and we don't want people to have to write this code over and over again. So this is something that we would get completely for free in a system like this, because we can use the methods that Hack already has for reusing code, like abstract classes or traits. And the list goes on. There are other things that line up quite nicely. For example, list types exist in Hack and in GraphQL in essentially the same form. Same thing for enum types. So these are some things that would work, but we also have some concerns. So no system is without disadvantages. And one open question here is what to do if there are situations where the type systems don't quite line up. So I have some examples from where that happens in Hack, but if you try to apply similar concepts to any other language, you'll probably come up with maybe the same, maybe different examples. So one example is union types, which are an important part of GraphQL, but don't exist at all in Hack. And then there are things like input objects, where the similar concept exists, but it's not quite the same. For example, there's no way to declare default values, which also people use a lot on input objects in our schema. So that's one thing that comes up. Another thing that comes up is that it's not always a good idea to just mix what is essentially a declaration of your public API with your internal code. A very, very valid concern. But on the other hand, sometimes the classes you have already are sort of a public API for your data model, and in those cases, we don't want to force you to write a second declaration just for GraphQL. It's nice that you can just annotate the existing one. So there's a trade-off here. I think we'll have to trust people that they would be careful about doing this right, and if there's some sort of internal class that shouldn't really be exposed as a public API, they'll try to extract the public API into a separate wrapper class or an interface or something else. All right, so that's what we're thinking about right now. And to conclude the talk, I'd like to just mention a few things that we haven't really tackled yet, but that sometimes come up in discussions and that we may or may not tackle in the future. So an interesting one is this notion of non-nullability. GraphQL allows fields to be non-nullable, in which case the server should guarantee that the value of the field is never null. Clients developers love this because then they don't have to do null checks in their code, and it's like they save a lot of boilerplate. It's just great all around. The problem is that on the server, life is not so easy. We can't really guarantee anything. Any field resolver, which is arbitrary PHP code, may throw an exception, and then we just have no value to put there. So the question is, how do we resolve this? Like, how do we allow server developers to expose non-nullable fields, but also allow them to actually provide some guarantees? That's one thing. Another popular topic is error handling. So the GraphQL specification actually provides a good way to do this. It specifies that the response should contain a list of errors. These errors may contain arbitrary metadata, so it's not infeasible that we will include something like a path to where the error happened directly there in the response. And the clients can do whatever they want with these errors, have some kind of super sensible, extremely nuanced error behavior. But the truth is that the clients don't really like to do this. They don't want to have a super sensible, extremely nuanced error behavior for every single GraphQL field in the response. So the question is, how can we provide frameworks or abstractions on either the server or the client side that make good error handling easy to do for client developers? So that's all I have. At this point, I like to open it up for any questions you might have. Thank you for listening. Yeah, question?
I also spend a lot of time trying to optimize.
The question is whether we have some kind of I think global context object that we pass to all the field implementations that they can use for things like fetching the currently logged in user. And yes, we have that. So I think the way there are multiple ways to do this. There's sort of the right way to do this, and there's sort of the way that we actually have to do this. The right way is that this should ideally be part of the parent object, which is always accessible. So like if you're a field on the user object, the user object would contain this context and then pass it down to any child objects. So that's sort of the right way to do that. So then the field resolvers have no other state besides the parent object and any arguments provided to them. So that's a nice, clean way to do that. In practice, this is not always so easy. So we do actually have a global context object. We call it the viewer context, and we make this context object available to any field implementations. And the way to do that, that's basically an implementation detail. I think there are multiple different ways to do that. What we would probably do in this proposal that I showed you with the attributes is that like if you include an attribute of this type, the viewer context, then the GraphQL framework would magically put the right thing there. So that's one way to do that. But if you have any chance, just do it the right way.
I've been thinking a lot of kind of like how I can mix proper arguments with context.
Yeah. Okay. Question? Yeah, I think sorry. You were first in the back. Yeah.
How do schema updates work? Like, do you ever have like a consistent schema?
Okay. Question is if we're doing any query optimizations like joins in SQL. That's a very good question actually. It does come up from time to time. We haven't really needed it as much as perhaps some other systems that depend on things like SQL, because Hack and HHVM have a very good model of asynchronous execution where things get automatically batched and then sent to databases together, and it provides that at a layer lower than GraphQL. So this doesn't come up very often, but it does come from time to time. And we have at least one place I can think of where we've been experimenting with this. We currently don't have a really good implementation, more of a slightly hacky one, where we give a specific field resolver a way to look ahead in the GraphQL query and do some optimizations based on that. So that's sort of a hacky implementation. Please don't do that, but it's just so that we can see if this actually helps. If it does, then we'll probably try to come up with a cleaner way to do that. I think there have been proposals in the community. Some of them were pretty good and interesting, like this notion of a two-pass execution where the first pass would be to gather all the information needed to optimize the query, and then the second pass would actually produce the data. But yeah, it's a bit of an open question still. Very good question.
Cool. Thanks. If you guys have any more questions for any of the speakers, please feel free to ask afterwards. And thank you so much for the talk, Jan. That was
Thanks.
awesome.